Hello everyone, this is Singh 𝐂𝐤 and today we are discussing how Discord stores billions of messages. There are billions of messages flowing across the servers among the different members of those servers. So how are these messages actually stored? These billions of messages actually stored in which database, how it is stored, how it is queried. We are only deep diving into all those details. So let's start into it. So first of all, like, which is the database which we use for storage? Cassandra is the database which we are using. Now why we are choosing Cassandra? Cassandra is your NoSQL database, right? Cassandra is your NoSQL database. Now we want to like deep dive into why particular this net Cassandra is being chosen. So first we have to understand about query pattern. So whenever we try to choose a database, we should think of like what kind of query pattern we are having, what kind of reads we will have, what kind of writes we will have, what is the ratio of these reads and writes. Is our database read heavy, is our database write heavy, and what kind of query patterns we will have. So thinking about these 2 points, if you talk about read and write pattern, like the ratio will be 50/50, so they are approximately equal. Your database is not read heavy, your database is not write heavy, they are approximately equal. Second point is like what kind of querying you are doing, right? Is the queries are too frequent, what are the amount of messages depending on the number of depending on the type of server which is created on the Discord. So considering three types of server which are being created on Discord, first let's say one is voice chat heavy. On a voice chat heavy Discord server, there will be very few messages, few text messages which are being shared among the members, because it is a voice chat heavy, so there are very less messages. Let's say approximately 1k messages per year. In this scenario, if we are trying to search for those messages, there will be random seeks on this causing this cache eviction, let's say, because since there are very few messages, one message will lie here, another message will lie here, third message will lie, there will be a lot of space. It will not be a contiguous operation. Okay, if we talk about private text chat heavy, okay, there are a lot of text messages, but there will be not there will be more as compared to voice chat heavy, definitely. But in case of private Discord servers, the number of members will be limited, so there will be good number of messages, definitely, but it will not be too much. So let's say we will have approximately 100k to 1 million messages per year. And in this scenario also, the search rate at which you are searching for messages will be not too frequent, so the data will not be present in disk cache. Why? Because it's not frequent. Okay, another one is large public Discord server. In this type of scenario, the number of messages are too huge, multi-million number of messages, and in this case messages are requested often, so usually present in disk cache. Okay, so if we like say like what kind of reads we are having, we will have random reads. Why? Because depending on the type of the server which we have, the pattern we will have are different. So the database which we are choosing should kind of support that, or should not be blocked on that. So it should support random reads, and our read and write ratio is 50/50, so they are approximately equal. Now what kind of requirements we are looking for? Like, we will also have our requirements. So what kind of requirement Discord has while they are choosing a database? So first is linear scalability. When we say linear scalability, there are two things. Whenever I try to add more nodes, let's say the number of messages has increased from billions to multi-billion. So in this scenario, I will have to add more nodes to my database to support that storage requirement, because I have to increase the disk space. Okay, so if I have to increase the disk space, it should be supported inherently. I don't want to worry about that. So it should be easily available. Another one is I don't want to be worried about the resharding. Okay, in case of SQL databases, what you face is you have to actually shard the data again and again, in case if you have to scale it up again, horizontally scale it up again, so you have to shard the data. So I want to take care of that from the beginning itself. I don't want to think about it after 1 year or 2 years when my data grows. Okay, so the first thing is linear scalability. It should be supported. Automatic failover, when we say, let's say you had multiple nodes. Okay, this is your database cluster, and in your database cluster there are multiple nodes. Now in case there is one node goes down, this particular node goes down, so another node should come up on its place and should be automatically handled. I don't want to have my own logic to be built on it so that I have to support that kind of operation. It should be built inherently. Low maintenance, when we say, should not require extra setup. Okay, it should be easy to configure and all those things. I don't want to be worried about anything about maintaining it. Basically operational cost of the database which we are keeping. Proven to work, when we say proven to work, it should be in use actually by any of the companies, any of the large scale companies. So any database I am choosing should be already in use. It's not like there is a new database in market which is very efficient and blah blah blah, so I'm not going to use that database because it is not proven to work. Okay, they are saying that it is very fast and all those things, but I don't know if it actually works. I don't have any numbers. I don't know any companies which are actually using it. So I want to select a particular database which multiple companies are using, which a use case like they also are storing billions of messages. I also have certain similar kind of requirements, so I want to choose that kind of database. uh, Good performance, it's like a basic thing. Whenever you want to choose a database, you want a good performance out of it. It could be write operation, it could be read operation. You want to be the job should not be the latency intensive. It should be able to be, it should be performed in the minimum time possible. Again, blob storage is not a solution, so we actually discarded blob storage. Because why? Let's say this is your server, so as and when new messages come, you have to let's start from scratch. So let's say this is your file. Okay, so new messages came, you write. Now another message came, you have to append the messages again. So in these scenarios, what you have to do is you have to deserialize that database or deserialize that blob storage and then append the messages to them. So there is kind of extra work and I don't want to do that extra work. So blob storage we are not considering. Open source, it should be open source. No dependency on third party, any database which is being completely managed, completely abstracted out. So I don't want to use that database. I want to use an open source database which is good, which provides good performance, proven to work, low maintenance and all those things. Okay, so all those requirements are being met by a database which is called Cassandra. Okay, Cassandra is a NoSQL database as we already discussed, and the requirements we had are related to random reads. So the Cassandra stores related data contiguously on disk, providing minimum seeks and easy distribution around the cluster. This we will discuss in some time, that how we are actually storing the data so that related data is stored contiguously and we don't our read operations are not intensive enough and they can be performed in minimum time possible. So how Cassandra actually works. Okay, how the data is modeled on Cassandra. So Cassandra is let's say this is your key, this is your value. Okay, now for that particular storage requirement, Cassandra, the primary key of Cassandra consists of two keys, right? This is your primary key. Now this primary key consists of two keys. One is partition key and another one is clustering key. Now what these both keys define is, let's say this is your Cassandra cluster. This is your Cassandra cluster and these are nodes. These are four nodes to start with, 1, 2, 3, 4. Now for a particular primary key, let's say my primary key is partition key is 1 and your clustering key is 3, 4, 5. So in this scenario, it will be stored on node 1 with a clustering key as 3, 4, 5. So on partition we are defining is on which particular node the data is storing, and this clustering key defines how actually stored in the rows. So it defines the sorting order. So when we say 1, 3, 4, 5, then 1, 3, 4, 6, 1, 3, 4, 7. So they will be stored. If I define ascending order, then it will be straight 1, 3, 4, 5, then 3, 4, 6, and then 3, 4, 7. So it's actually easier to read this way. If I write a query according to this, so it will be very faster, right? So this is how our actually data modeling look like. And if we talk about the table which we created to store the messages, channel ID, message ID, these all are the columns, and your primary key is combination of channel and ID. This is a compounded key, channel ID and bucket. We will discuss in some time why do we need a bucket. okay, and message ID is your actual message ID. It's basically a snowflake. Snowflake is a Twitter library which is being used to generate a number basically, okay. This is timestamp, worker number, and sequence number. So I will share the links with you related to Snowflake. You can read more about it and get the details how it actually works. So it's, you can think of a simple library which gives you a number which you can use as a message ID. Okay, and your clustering ID is message ID stored in the descending order. Moving beyond other details about Cassandra. So Cassandra supports partitions till 2 GB. You will see warnings if partition is greater than 100 MB. Large partition should be avoided. Why? So when we say I am creating a primary key, so you created a primary key with help of partition key and clustering key, right? So the earlier, let's say we started with channel ID, like this code actually started with channel ID, and during the experimentation they figured out that the partitions size is becoming too huge, they should reduce it. Then they introduced this bucket concept. So channel ID, let's say for a particular channel there are a lot of messages, so the partition could definitely exceed 100 MB data, right? So actually Cassandra supports 2 GB, but there are warnings if the data grows beyond 100 MB, and it should be avoided. There are certain reasons for it. Why? Let's say consider example that a particular node in my cluster has went down, or a new node has to be added in my cluster. So in this kind of scenarios, during cluster compaction or cluster expansion, it puts a lot of GC process because your partition is too huge to handle. So this is the one reason. Another reason, it cannot be distributed around the cluster. Why it cannot be distributed? Because your single partition can hold lot of data, right? The data will be distributed in case your partitions are small. So let's say partition 1, partition 2, partition 3, there are only 100 MB, 100 MB. So in this case the data can be actually distributed across the cluster. But if let's say the partition is too huge, then it can actually hold lot of data. I don't have to be kind of distribute the data across the cluster, because a single partition is holding lot of databases. Let's say for a particular server there are lot of messages, and it can hold, single partition can hold 2 GB of messages. So it will grows and grows, it will grow and grow right? So to make sure it is less than 100 MB, the data is bucketized. How data is bucketized? It is derived from message ID, which is actually your snowflake, and to sample code. I will again share the link with you of the Discord blog, but if we check about how the sample code is written, it's somewhere here. Yeah, so this is the sample code which is written on how you can actually derive your bucket, right? So this is the code which you can refer, and this is your table which we discussed. Like the earlier Cassandra started with this table. Your primary key was channel ID and message ID, and then further uh, due to the issues observed, due to that your partitions are becoming too huge, the primary key was compounded to include bucket in itself. Okay, so now we have stored the data, now we have to query this data. Okay, so we have stored the data, now we have to query it. So how we will query it? So you have to you will generate the bucket from current time to channel ID. Okay, channel ID is also a snowflake which is older than the first message. Definitely the first message you are creating, it should be older than that. And sequential query message for a certain threshold of messages. So one thing is definitely that let's say this is your server. So in a single query, you don't want to get all the messages of it, because the user will not read all the messages in one go. So let's say you read these messages, and as in you scroll up, you can query for more messages which can be displayed again. So the messages can be queried for a certain threshold, and you will sequentially go on querying them as and when user is scrolling the let's say your chat stream, right? Now once we have chosen Cassandra, we have actually stored the messages, then we tested in our gamma, and then after prod launch we have observed some issue. One issue was author ID is null, right? Now your author ID is like who is actually the author of messages. Okay, author of message, who is actually the author of messages. Now can there be a scenario that a message don't have a author? Because actually message has to be associated to a author. So how it could be null, right? It's a big issue. it should not be a null because it's a required parameter. So either there is some fishy in our code, there is some issue in our code, there is some bug in our code, or there is some wrong with Cassandra. How database internally works, I don't know right now, so I have to figure out that. So why this issue occurred? Issue occurred because Cassandra is a AP database and it occurred due to eventual consistency. So Cassandra, since mainly is a AP database, if we talk about CAP theorem, consistency, availability and partition tolerance. So AP database means it's prefers availability or consistency. So Cassandra prefers availability, that node should always be available. If the data is if it is not strong consistent, then it's fine. I'm okay with eventual consistency support. So in these kind of scenarios, how it actually caused the issue. So let's say let's consider a scenario where you have a message written, right? You have a message written. Let's say this is your message ID, and in that particular message, this message was present on your particular partition, this particular message. Now user A edits this message, and at the same time user B, what it does is delete this message, right? Now this is happening at the same time, and if we talk about how writes happen, they are absurd. You will end up a row with all data missing except primary key and text. Why it happens is because in this scenario, these two users, like for a particular message, like this might happen, right? In a particular Discord server, two users are performing operations on a single message. So this could happen. It actually happened. The issue was observed in production of Discord. So there were two resolutions which were thought of. Either you write whole message back, right, when adding the message. So there could be more chances of conflict then, because you are rewriting the message again. Figure out the message to corrupt and delete it. Like actually figure out the message ID of the message which is corrupt, and you can delete it at your end. Okay. So in this scenario specifically, if any of your required column is null, in this scenario author ID was null, so you can actually delete this message. This write operation is slow. I am just reading this blurb. So this write operation is slow. Cassandra is eventually consistent and don't delete data immediately. Delete operation also need to be replicated to other nodes as per requirement, even if nodes are temporarily unavailable. This I will explain you with the example. So this same scenario, right? A user A edit the message and user B delete the message. If we discuss this in little bit detail, so I will again draw the diagram. So this was your particular message. This is your user A. This is your user B. Handsome user. And this is very handsome user. So this particular handsome user is editing the message, and this particular very handsome user is deleting the message, and this is happening at a particular time x. Now what Cassandra can do in this case, edit message is edited, and Cassandra works on last write wins algorithm. So the last operation which is being which happened on that particular block of message, in this scenario message on any write block. So last write wins algorithm is used by Cassandra, right, to resolve the conflicts, any of the conflicts which occur. In this case conflict would occur definitely because both the operations are happening at the same time. So in this scenario, let's say this message was present on two nodes. This is your Cassandra cluster, and this message was available on two nodes. So you can resolve the conflict with last write wins, right? That is sorted. Now what if this particular node was unavailable at that time? Okay, this was available, so it was actually processed at this node that this particular message is deleted, and on this particular node this message was this particular node was not available at that time. So in this scenario, what can happen is when this node comes up, it will see that a particular message is not available on this, it is deleted, and it is present on this, so it will try to sync with it. Okay, so the message can reappear on this node. In this scenario, you are actually reflecting back the deleted message, so this can create more issues. So to resolve this, to handle this kind of scenarios, Cassandra works on concepts of tombstone. Okay, tombstone. So whenever a delete operation is carried out, it do not actually deletes that message but just puts the marker on it. So let's say this particular message is deleted, it will not remove it from the actual storage, it will just put a marker in it, let's say deleted. And these are called tombstones. So whenever you are querying the data, if there is a marker present on it, it will not go, like it will not return in the results. So this is the concept of tombstones. Now how it can cause issues, let's discuss that. So we were here. Cassandra achieves this by treating deletes as a form of write called tombstone, which we already discussed. I hope you understood it. I will also share some documents with you, more blogs with you, how tombstone actually work and what are different kind of tombstones, what are different scenarios. Like one scenario we discussed here, in case of single write, there could be possible that you deleted the complete data of a partition. Those kind of tombstone are called range based tombstones. There could be other tombstone basing TTL. Let's say you have configured, like the data which you have stored have specific TTL defined, that the particular data should be deleted after 45 days. So the TTL tombstone can occur. So these kind of tombstone, other details I will share with you, one blog link which we shared with you in the video description. If you want to read more on this, you can refer that. This we also discussed that it can skip tombstone on read operation, tombstone leave for 10 days. So this is the default time period which is configured in the Cassandra. You can reconfigure it as per your requirements. In summary, on write if non null value is y. So to avoid the null issues, to avoid the null scenarios, what we can do is we can only write the data when there are non-null values in our record. So to reduce the issue, of tombstone, what you can do is you can do two things: reduce the lifetime of tombstone, so Discord reduces to 2 days, and track empty buckets and ignore them. So you can actually track the empty buckets which are present and ignore them while on your read operation. This will help to improve your queries. So this is all about how Cassandra stores billions of messages on their database servers, like which database is used, why it is used, what are the issues, what were the issues which were actually being observed, how it is scalable. And if you want to read that complete blog, you can read it here. The link will be shared with you in the video description, so you can go and give it a read. We will meet again in our next video where we'll be discussing how these messages are actually indexed on Discord servers. So once you have stored these billions of messages, if you want to provide a search capability on top of it, any kind of search capability, if you want to search among the messages, how this data can be actually indexed, we will be discussing in our next video. Till then, stay safe. Tata, bye bye.